and to take care of these power series, and you shouldn't have any difficulty at the end. Okay, so let's see what's going to be the power series. See, the power series is a kind of generalization of the, we can say, the polynomials. So if we give you a polynomial, polynomial start with what? Something like x squared plus 2x plus 1. It's quadratic. Then you get x to the third, okay, x cubed plus 5x squared minus 3x plus 1. That would be the cubic, etc. So we are going to introduce kind of sequence type of the polynomials. Okay, so let's give you the definition of the power series. Okay, so suppose we have a sequence of numbers. Use a special notation for this section. Okay, suppose the C0 or C0, C1, C2, up to the Cn, etc. These are going to be is a sequence of numbers. Is a sequence of numbers. And then generally we start with the C0. Okay, sequence of numbers and x. Okay, and x is a given variable. Is a given, is a real variable. Okay, is a given variable. If this is going to be the case, then you see this expression, sigma of Cn x to the n from 0 to infinity, which is equal to the, okay, if you put Cn equal to the 0, that gives us C0, okay, C0, C1x, C2x squared, etc. Cn x to the n. This is going to be called, is called a power series. Okay, a power series. You can say that's the power series of x, or the power series of the powers of x. Okay, so for example, see, for example, if you have something like sigma of x to the n, it's very famous one that we did it before, from n equal to the 0 to infinity. So this would, the first thing would be 1 plus x squared, different power of x. Okay, so this is going to be the one, is a power series, is a power series. So as you can see, x is a variable. If we replace x by a number, and the resulted series is going to be convergent, we say that this power series is convergent at that number. So since there is an x, so the convergence or divergence of the power series depends on x. Okay, so look at this this example. So what we'd like to do, we'd like you to find, okay, find the values, okay, values of x for each power series. Okay, each power series is going to be convergent. So for some values, you may get a convergent series, or some values you may get a divergent series. Okay, so let's check. You see, the first one is going to be a famous one in future, sigma of x to the n over n factorial, n from 0 to infinity. So if you put, if you put n equal to the 0, so that give you 1, you don't have to expand it. I just expand it so that you can see it. So it's going to be 1x 1 factorial, x squared over 2 factorial, etc. So in order to find out where this function is going to be, or this power series is going to be convergent, usually using the ratio test. Remember the ratio test that we did before. So for the solution, so apply the ratio test. Apply the ratio test. Remember, for the ratio test, you have to find the limit of. So it's a an plus 1 over an. Since we don't know, so you know that we use the ratio test for the what? For the positive number. So what we can do, we can use the absolute value because there is a x here, so that to make sure that, you know, because with the absolute value, go to the absolute convergent, but you know that if a series is absolutely convergent, it's also convergent too. So we use this, okay, we use the absolute value of an plus 1 over an, okay, when n goes to infinity. So this is going to be limit of the absolute value on the top. An plus 1, you replace the n by n plus 1. So that give ax to the n plus 1 over n plus 1 factorial. And this is going to be x to the n over n factorial. Okay, the absolute value. N goes to infinity. So we're going to simplify it. It's going to be limit of the absolute value of the first fraction, xn plus 1 over n plus 1 factorial, times the reciprocal of the bottom, which is n factorial over x to the n. Simplify it. So when you simplify it always for the x's, this is x to the n, this is x to the n plus 1, so the leftover of the x would be x. And you can pull out this x out of this, you know, out of this fraction. If let's do it, and I do it. And for the n, this is n factorial, n plus 1 factorial. You know that n plus 1 factorial is n factorial times n plus 1. So the n factorial and the n factorial cancel out. So the leftover on the top, look at this one. So it's going to be the absolute value of on the top. You get x. Okay, down the bottom, you get n plus 1. N plus 1 when n goes to infinity. So there's going to be a leftover of the x all the time. You can pull out the x because the limit is depends on n. So it's going to be the absolute value of x, the limit of. So the leftover is going to be 1, n is a positive number over n plus 1 when it goes to infinity. And you know that this is going to be absolute value of x. This limit would be 0 times 0, which is equal to the 0. So the limit of an plus 1 over an, n goes to infinity, is equal to the 0, and the 0 is less than 1. You know that in the case of the ratio test, if the ratio is going to be less than 1, the series is convergent. If the ratio is going to be, okay, there's going to be less than 1 is convergent, it's going to be greater than 1 is divergent. So in this case, as you can see, for this case, so it's going to be less than 1, regardless of whatever number you have for x. So it's going to be less than 1 for all, okay, for all values of x. So this basically means the power series. Okay, so the power series sigma of xn over n factorial, n from 0 to infinity, is convergent. Okay, is convergent for all values of x, or values of x. So you know it's going to be convergent for every numbers, because you know if you replace x by any number, the result is going to be a convergent series. Okay, so that's case 1, that the series can be convergent for forever. It's a very special series. We're going to see it in a minute. What is going to be the exact series we talk about it. That's case 1. The case 2, see the case 2 is going to be this series, sigma of x to the n from 0 to infinity. Think about it as a geometric series, but let's think about it as a power series. Again, for the solution, we are going to use the ratio test. It's going to be limit of the absolute value of an plus 1 over an, and goes to infinity. So this would be the limit of an plus 1. We just replace the n by n plus 1. Divided by what? Divided by x to the n. So these x's would simplify. So the leftover on the top would be x. There is no n. So that gives you the limit of the absolute value of x when n goes to infinity. So if you pull out the absolute value, the leftover is 1. And there is no n. So the limit would be 1. So that gives you absolute value of x. Okay? Now, you know that if the ratio test is less than 1, the series is convergent. So you force this one to be less than 1. Okay, so if this is going to be less than 1. Okay, so now you argue that if absolute value of x would be less than 1, then the series converges. Okay, it's the power series, and from 0 to infinity is convergent. And you know that it's the geometric series. In case of geometric series, when the common ratio is less than 1, then in that case the series is going to be nicely convergent. Okay, so this is going to be the case for. So the difference between these two is the first one was convergent all the time, but this one there is a number. That number is 1. If the absolute value of x is less than 1, this series is convergent. So this means if you replace x by 1/2, that gives 1/2 to n. You know that is a geometric series, common ratio 1/2 less than 1, it's convergent. But if you replace the x by something like 3, that gives it 3 to the n. Is a geometric series with a common ratio of greater than 1, it's going to be divergent. So in this case, that's going to be the case for the x, okay? So that's the second example. The third one is this one. Look at this one. It's very famous series, you know, it's in any calculus book. So it's a sigma of n factorial x to the n. And we want to know where this series is going to be convergent. Again, go with the ratio test. Okay, if you go with the ratio test, what's going to be the limit of an plus 1 over an when n goes to infinity? So that gives you the limit of the absolute value on the top. Replace the n by n plus 1, so that gives n plus 1 factorial x to the n plus 1. Okay, divided by n factorial x to the n when n goes to infinity. Okay, so it's going to be the case. Again, we simplify it by x to the n, that would be 1. That x to the n plus 1, the leftover would be x. Okay, so this is n factorial, n plus 1 factorial. So that would be simplified. This is n factorial times n plus 1. So that gives n plus 1. So this limit would be basically is equal to the limit of the absolute value of n plus 1 times x. So we pull out the x because the limit depends on n. So that gives you the limit, that gives you the absolute value of x times the limit of n plus 1 when n goes to infinity. You know that when n goes to infinity, this limit is infinity. So it depends what would happen for the x to find this limit. So we are going to consider two different cases, you see. The case is that if this x is not 0, if x is not 0, then this would be a number. And this limit is infinity already. So it's going to be 2, 3 times infinity. So the result would be infinity. But if x is equal to the 0, if x is going to be 0 right at the beginning, you are going to have a, okay, if if you put x equal to the 0, you see, if you put x equal to the 0, so at the beginning, this would be 0 times the number, which is always equal to the 0. So you're not going to have anything. If x is 0, we get 0 series, we call it. Okay, so it's going to be 0, so that gives you 0. Don't say 0 times infinity. The series does not exist over here. Okay, so this means this series is convergent only at one number when x is equal to the 0. Because if you put x equal to 0, you have the 0 series. Okay, so because the infinity is bigger than 1. So for this one, you get a divergent series. But so this means that the power series sigma of n factorial x to the n from 0 to infinity is convergent. Okay, it's going to be convergent only for x equal to the 0, only for, okay, convergent only for one number, only for x equal to the 0. Okay, so these three examples would tell us, would give us something. And that's the case that if the power series is given to, there are three possibilities. You see, look at this one. The first possibility is that this series is convergent forever. The second possibility, okay, is going to be, let's take this one. This series is convergent only for one number, x equal to the 0. The last possibility is going to be, there is going to be a number, in this case 1. There is going to be a number such that if the absolute value of x is less than 1, this series is convergent. If the absolute value of x is bigger than 1, this series is divergent. Okay, it can be proved that this is the only case that we have, so we write it down as a theorem. I can prove it. So the conclusion, that was something for you not to be surprised when we write it down. Okay, so it's not just a coincidence. Okay, you can have it all the time, and this is going to be the case. The theorem is for any, okay, given a power series, okay, for any given power series, one of the following, okay, it can happen if you like, or for any given series, one of the following, okay, is going to be, is possible if you like. Okay, the first one is going to be the power series. Okay, for the any given power series, let's say sigma of Cn x to the n from 0 to infinity, one of the following is happen. And the first one is just the power series is going to be convergent. Okay, it converges for any real value, okay, for any value of x. That's the first condition. Okay, the second condition is it converges for one value, x equal to the, okay, it converges for x equal to the 0 only, if you like, or it converges only for one number, or x equal to the 0. The third one is the big one. The big one is there is a positive number, call it R. Okay, there is going to be a positive number R such that this series, okay, this series converges for absolute value of x less than R and diverges for absolute value of x greater than R. Okay, that's going to be the third case. If this is going to be the third case, in this case, R is going to be called, Okay, R is called the radius, okay, the radius of convergence. Convergence of the power series of the, you have to know this expression because we have to do it over and over and over. Okay, in this case, R is going to be called the radius of convergence of the power series. Okay, so this is going to be radius of convergence of the power series. Then we can have, note also, you see the same, note that the power series, you see, if you open up this one, absolute value of x less than r, x would be, okay, x would be between negative r and r. So know that the power series is going to be, is convergent on the following, okay, on the following, okay, on one of the following, if you like, okay, on one of the following, one of the following interval. You see, you may have the open interval negative r and r. You may have, negative r and r close. You may have a bracket on both sides. You may have a bracket on this side. Okay, these are going to be called the interval of convergence. Interval of convergence. It's like a function that you have the domain of the function. Now you have a kind of domain of, okay, now you have the domain of the convergence of the, okay, of your power series. So when you find the radius over here, then you have to put x equal to the r and x equal to negative r, and check to see that you may get, you may get a convergence series again. Then you can, open interval is always the case, but the question is whether you get a, okay, you can have something better in this case. So I give you another one, and this is your job. You are going to see it. We are going to extend it in a minute a little bit, okay? But this is what you are going to do for us over and over and over. So what we'd like to do is we are going to ask you find the radius and interval of convergence of the power series series. Okay, and the power series is this one, sigma up -1 to the n, okay, x to the n over n plus 1. That's the case when n starts from 0 to infinity. That would be your main job, to get this one through. Okay, so you have to use the ratio test. You find the limit of a n plus 1 over a n. You force it to be less than 1 because of that, the ratio test. That would give you the radius of conversion. Let me do it. Okay, that's going to be one solution. Carefully form this one. What is the limit of the absolute value of a n plus 1 over a n goes to infinity? Replace all the n by a. You can make a shortcut, but it's the first one I write it down for you, but we can write down in short form. You see that will happen to the top. Replace the n by n plus 1. So this is going to be -n to the n plus 1, x to the n plus 1. You replace the n by n plus 1, that gives you n plus 2. Down the bottom would be negative 1 to the n. That gives you x to the n plus 1. When n goes to infinity. Since we're using the absolute value, you can forget about this negative 1 to the n. All will disappear. Then you see one of these x would be cancelled out to get the x on the top. You can pull out this x, you see, quickly simplified as, because the limit is on n, absolute value of x, now the limit of n goes to infinity. Now the leftover on the top would be 1 over n plus 2. You see, I write down for you, 1 over n plus 2 on the top, 1 over n plus 1 down the bottom. Since n is positive, you don't need the absolute value. Okay, so the absolute value go for x. So this would be absolute value of x, the limit of, you know that, you write the first one, flip the second one, it's going to be 1 plus n plus 2, and that would be n plus 1 over n, and goes to infinity. This limit would be 1, because the powers are the same. So that gives you absolute value of x times 1, which is absolute value of x. Okay, so quickly simplify it. You see, quickly you put this absolute value of x, you drop this, okay, because it's the absolute value. So it's going to be 1 over n plus 2. The other one is 1 over n plus 1, use the reciprocal. So the n plus 1, n plus 2, when it goes to infinity, the limit would be 1. So we get the absolute value of x, okay? So I rewrite it over here to see what we are going to do next. So what we have is, we got the limit of the absolute value of an plus 1 over an. Okay, when n goes to infinity, it's the absolute value of x. You see, whatever you have, because using the ratio test, by the ratio test, if this result is less than 1, the series is convergent. So you argue that by ratio test, the series, the power series converges if the absolute value of x is less than 1. You see, sometimes you may have to do something to get the absolute value of x isolated, right? For this problem, it's already nicely given to you. So as soon as you write this one would be radius of convergent. Okay, so r is equal to 1, the ratio, okay, radius of convergent, and the series is convergent, and the series, open it up, converges on this interval. You see, this is absolute value of x is less than 1, so that gives you x between -1 and 1. So it's going to be convergent on open interval of -1 and 1. Remember, you're looking for the interval of convergent. As soon as we get the radius over here, we open up the absolute value. So x would be between -1 and 1. But you have to check the endpoint. Okay, you are going to check x equal to the -1 and x equal to the +1. So you may get a closed interval. So for this definition, always you get the open interval first. And you have to check the endpoint to the left and to the right. Okay, you go back to the series and you substitute to the original one. X equal to the -1. Go to the power series. You see, this is your power series. You replace x by -1. Then you check to see if this result is a convergent series or a divergent series. So it's going to be, you're going to get the limit of, that was a -1 to the n. You replace the x by -1, so that gives a -1 to the n too. Okay, and over here you have n plus 1. Now you have to simplify it. N from 0 to infinity. You see, -1 to the n times -1 to the n would be -1 to the 2n. So that gives a limit of -1 to the 2n over n plus 1. N from 0 to infinity. Okay. But you know that -1 to the 2n would be a positive one because the power is even. So that give you what? That give you the limit of 1 over n plus 1, n from 0 to infinity. You know that this is a power series, n equal to 1 is divergent. So is a divergent. You don't need to explain it more. Just say is a divergent P series. Okay, so the power series is divergent for x equal to -1. Okay, so this means you cannot add this one to this interval. The power series diverges when x equal to the -1. Okay, you're not done. You have to check x equal to +1. So when x is equal to +1, you go to your series, so we get -1 to the n, 1 to the n over n plus 1, n from 0 to infinity. 1 to the n would be 1. That would be 1, so you end up with what? It's going to be sigma of -1 to the n, -1 to the n over n plus 1, n from 0 to infinity. Remember, this is alternating harmonic series. Alternating harmonic series is convergent, and we accept that right away. So is a convergent. You use everything you learned for a power series for one of these problems. So it's a convergent, alternating, remember, positive, negative, positive, negative. So it's a converging, alternating series. So the power series is convergent at x equal to 1. Okay, the power series converges when x equal to 1. So what's going to be the conclusion? Okay, conclusion is that the radius of convergence is 1. Okay, interval of convergence. Okay, interval of convergence was a -1, 1. But at 1, it's convergent. You have to break it, you have to close it. And -1 is this, not open. So that would be the result. The radius is 1, and the domain of the convergence is -1 and 1. Okay, so it's very nice procedure. It takes time, but the result is quite nice one to get there. So this means if you want to work with this one, you have to make sure that use the numbers between -1 and 1, because the result is going to be a convergent series. Otherwise, it's not going to be convergent, and you cannot use it. Okay. Now you see, we can stay with this one, or we can extend it a little bit. The extension is going to be, if we're going back to our power series, you see, this series that I defined for you is x to the n, is the powers of the x. But sometimes you may need the power of something else. Okay, x minus 1, x minus 2, x minus 3. So that would be a little bit more popular for the application in future. Okay, so everything can be extended a little bit. It would be a little bit more to work with, but it's worth it. Okay, so that was just the warm-up. To get these numbers, we get one question on this, but the extension of this definition that we're going to have. Okay, so what's going to be the extension? Because later on you will see in application in science, you may be interested in the not powers of the x, powers of something else, x minus 1, x minus 2, x minus 3. Okay, so we give you a more general definition of the power series. So we give you a remark. So that was, easier to apply. But you have it. We are going to have a name for it in future. We call it Maclaurin series. And the one that I'm going to talk about, we're going to call it Taylor series. So we're just building up, something very big for future. So in general, we're going to extend everything in general. general. Now bring another number. If A is a number, okay, then look at this one. Sigma of Cn x minus A to the n from 0 to infinity. Again, you know, the first term is going to be C naught. Next one is going to be C1 x minus A. Then we get C2 x minus A squared, etc. Again, it's a power series. You can x minus A, you can call it Z. X minus A. If you call it Z, that gives C and Z to the n. So it would be power series of Z. But this is going to be called, okay, this is going to be is the power series, or a power series sometimes they say about x equal to the A, or they say centered at x equal to the A. Okay, powers of x minus A, different names for this. Okay, so this is going to be a power series about x equal to the A. Okay, if this is going to be the case, in this case, okay, if there is that number or that we talk about it, if there is a positive number or such that the series, the power series converges, okay, when absolute value of x minus A less than r, and diverges when the absolute value of x minus A is greater than r, then as we talk about it, r is called the radius of convergence. The radius of convergence of the power series, power series. It's a little bit more general, and you will see the advantage of this type of argument when we get more serious about this type of this type of problems that we're going to have. So again, we have to check an example, okay, of this new format that we talk about it. Again, you are going to have some for the applications that we will see. Okay, so let's check another one. So this is going to be example. The same thing. What we would like to do is would like you to find the radius. Okay, radius and interval of convergence. Interval of convergence. Convergence of the power series. Okay, let's check another one to see what is going to be the case that we are going to have for this group. Okay, so let's try this one, something similar to the one that I did, but I changed it a little bit. You see, that's one. We want to know what's going to be the limit of convergence. -1 to the n. Okay, -1 to the n, and this is going to be, let's say, x minus 3 to the n over n plus 1. It's very similar to the one that I did. I wanted to compare them together. Okay, so it's going to be the power series which is centered at 3. Again, the same thing that we talk about it, just say ratio test, solution, apply the ratios test, limit of the absolute value of an plus 1, and goes to infinity. Okay, so this is going to be equal to the limit of, I write this one again for you. It's going to be negative to the n plus 1. Replace everything to the n plus 1. That would be n plus 2. So that gives negative 1 to the n, x minus 3 to the n divided by n plus 1. N goes to infinity. This negative 1 to the n would disappear. That's x minus 3 to the n. You see, there's going to be only one left over because x to the negative 3 to the n would disappear. So you pull it out. You see, pull out the absolute value of x minus 3. Write the leftover, the limit of. This negative 1 to the n would be out. That gives you 1 over n plus 1. 1 over n plus 2 times the reciprocal of the bottom one, which make it to the n plus 1 over 1. N goes to infinity. Because the limit of the leftover would be 1. So this is going to be absolute value of x minus 3. The limit of n plus 1 on the top, n plus 2 on the bottom, n goes to infinity. This limit is 1 because, you know, they have the same power. So it's going to be absolute value of x minus 3 times 1, which is absolute value of x minus 3 again. Okay, then by the ratio test, you force it to be less than 1. Okay, now we say that by the ratio test, the series converges, when the absolute value of x minus 3 is less than 1. As soon as you make it less than 1, that gives you the radius of convergence. Radius of convergence is 1. You open it up to get the interval of convergence. Okay, because of the ratio test, the ratio test will tell you that if this result is going to be less than 1, the series converges. Otherwise, it's divergent. Okay, so I put it over here. So this means, so I write down what we did, x minus 3 less than 1. So quickly, this means the radius of convergence is 1. You get the radius of convergence. Now you open it up. Okay, is 1, and the series converges when you see that give you x minus 3 between 1 and negative 1. Open up the absolute value, move the 3 to the other side, add. So x would be between 2 and 4. Remember, you are looking for that interval. So this means that the series converges. The series converges on this interval of 2, 4. You are looking for the interval of convergence, but you are not done, because the ratio test, when this is equal to, you know that it may be convergent or may be divergent. So that's why you have to check. Again, you have to check the series for these numbers. For x equal to 2 and x equal to 4. You have to check whether your series is going to be convergent or divergent for this one. Okay, go back, substitute. Remember, this is your series number. That's x minus 3 to the n. So you have to check the 2 and the 4 here. So we are going to check. Okay, x equal to 2. Go to the series, substitute, that gives sigma of negative 1 to the n. That was x minus 3, 2 minus 3. 2 minus 3 to the n over n plus 1, n from 0 to infinity. So 2 minus 3 would be negative 1. So that gives a sigma of negative 1 to the n. That gives a negative 1 to the n over n plus 1, like the one that we did. You see -1 to the n times -1 to the n would be -1 to the 2n, which is going to be a positive 1. So that gives a sigma of 1 over n plus 1. You know that this is divergent P series. Is a divergent harmonic series. Divergent P series. So we didn't get anything for x equal to 2. And you have to check x equal to 4. X equal to 4. Again, you go to the series, substitute -1 to the n. That gives you 4 minus 3 to the n over n plus 1. N from 0 to infinity. 4 minus 3 would be 1. So that gives a sigma of -1 to the n. So that gives you 1 to the n. N plus 1. 1 to the n would be 1. So that gives a sigma of -1 to the n. 1 over n plus 1. And we talk about it. It's an alternating series and it's convergent. Is a convergent, okay, alternating series. Alternating series. So what's going to be the conclusion? So it's convergent at 4, but it's not at 2. So you are going to close this interval. So the conclusion, the radius of convergent 1, interval of convergent 2, 4 close. So you have to close it at, at 4, but you leave it open at 2 to give you that, that number. Okay, this is this is where you are going to, how you're going to operate to get, to get these numbers, the conversion. That's your job. You have to check this, the interval of convergent. Later on, when we get these numbers, then we can introduce the function, and we do quite a lot. Okay, so you got to be patient to be able to get through this part, which is very, very important one. So I'm going to give another one. This is a little bit more technical one. So get practice quickly to get these ideas, because whatever you want to do, you see, from now on, you can do it only when the series is convergent. So you have to check to see that, okay, that domain of the convergence is the one that we are going to be interested in. Okay, let's check another one. The same thing. So I'm going to check this. Let's call this one number 1. So I give you this number 1. So I give another one. This may be a little bit different. Okay. So the series is this: sigma of 3 to the n times x minus 2 to the n over n factorial, n from 0 to infinity. Okay. So we want to check whether what is the radius of convergent and okay, the interval of convergent of this series. The series is about x minus 2. Okay, so let's go for it. Limit of the absolute value of an plus 1 over n goes to infinity. I'm going to shrink it quickly. See, I told you that, this is one leftover of this x minus 2 would be out. We get absolute value of x minus 2. Limit of n goes to infinity. You see the top when n goes to n, replace the n by n plus 1, that gives you 3 to the n plus 1 over n plus 1 factorial, multiplied by the reciprocal of the bottom, n factorial over 3 to the n. You see, quickly we write, and you don't need any absolute value because these are all positive. Okay, because that gives x minus 2 to the n plus 1 over x minus 2 to the n. You simplify the leftovers, x minus 2. So the top would be 3 to the n plus 1 over n plus 1 factorial. And the bottom one would be 3 to the n times n factorial. So you write the top one, multiply by the reciprocal of the bottom one. That will help you quickly to take care of it. Now simplify. 3 to the n and the 3 to the n plus 1, there's going to be a 3 on the top. N factorial, and n, you know that this is going to be n factorial times n plus 1, so the n factorial would be out. So what's going to be the leftover? Is the absolute value of x minus 2 on the top, on the inside. The top would be 3. The top would be 3. The bottom one would be what? The bottom one would be n plus 1. When n goes to infinity. You know that this limit would be 0. It's a problem because the degree of the bottom is higher. So that gives you absolute value of x minus 2 times 0. Times 0 would be 0. You see? 0 is always less than 1. So what does it mean? This means this series is convergent forever. Okay, so the series, the power series, because nothing to do with the x. You see the power series? The power series converges for all values of x, all values of x. You see that would happen. So what's the radius of convergence? In this case, we say the radius of convergence is infinity. Okay, so this is the way we write down. We say the R is infinity. And the interval of convergence is a negative infinity and positive infinity. Okay, so it's a very special case that it may happen. So be ready for it. Okay, because this is going to be 0. And there is no x here. It's 0, 0 is always less than 1, regardless of any x. So this means this series is convergent forever. Convergent forever. So in this case, we say the radius of convergence is infinity. The radius of convergence is infinity, and the interval of convergence would be all real numbers, negative infinity plus. Okay, so don't be surprised. Okay, now I should give you one more. The one which is going to be a little bit more technical one is this one. I have a couple of them, but I want to give you something. Okay, I'll give you this one. This is a little bit more, but we need to know it. Okay, how about this one? Sigma of. Okay, it's going to be sigma of, we get 2 to the n to the top, 2 to the n. Okay, and this is going to be x minus 3 to the n. Okay, and the bottom one, that's it. The square root of n plus 3, make it more exciting. N from 0 to infinity. Let's see what is special about this one. It's a power series about x minus 3. You want to find the radius of convergence and the domain. So go over the ratio test again. Okay, there you are. Limit of the absolute value of a n plus 1 over a n. Okay, n goes to infinity. So I'm going to shrink it again. You see, look at this one. This is x minus 3 to the n. It's going to be to the n plus 1 over n. So the leftover is just one of them. This would, x would disappear. Then the limit of n goes to infinity. When you replace the n by n plus 1, make this one to the 2 to the n plus 1. And that would be n plus 4. Multiply by the reciprocal of the bottom one, which is going to be radical. N plus 3 over 2 to the n. Okay, quickly you can take care of it. Okay, so the x minus 3 to the n plus 1 and to the n, you simplify, the leftover would be one of them. Then this is going to be 2 to the n plus 1 over n plus 4 divided by 2 to the n over radical n plus 3. You write the first fraction, multiply by the reciprocal of the other one. Now simplified further, 2 to the n, that's 2 to the n plus 1, so we get a 2 on the top. Okay, you can pull out these 2 times it, so it's going to be 2 times the absolute value of x minus 3, and this would be the limit of, on the top we get the radical n plus 3, down the bottom we get the radical n plus 4, n goes to infinity. You see the powers are the same. When you shrink it, The top would be radical n and the radical n, which is equal to the 1, because the degree are the same. So this is going to be 1. So the limit would be 2 times the absolute value of x minus 3. Okay. Now you force it to be less than 1 again. You see, because this is the ratio test. So again, by ratio test, the series, the power series converges, look at this one, when this result 2 times the absolute value of x minus 3 is less than 1. Because if the result of the ratio test is less than 1, your series is convergent. If it's greater than, is y. But you want to find the radius, okay? So this, you have to isolate x minus 3 to get the radius of convergence. Okay, you divide by 2, so that gives you half. Now half is the radius. Okay, so r is equal to the 1/2, because the series is about x minus 3. You should have the absolute value of x minus 3 to be less than r. So r is 1/2, and then you open up to get the, okay, the interval of convergence. And the series converges for, open up, x minus 3 less than half and greater than -half. Add 3 to both sides. This is going to be 3.5. 3 plus 1/2, which is a 7/2. You subtract, this is going to be 3 minus 1/2, which is a 2.5, which is a 5/2. Okay. I just add 3 to both sides. You see 1/2 plus 3 would be 3.57/2. Okay, and this is 3 plus 1/2. And the 3 minus 1/2 would be 2.5. So 5/2, 7/2. So the series is going to be convergent. So far the series converges on open interval of the 5/2 and the 7/2. And you have to check the endpoint of the interval. Check x equal to the 5/2 and x equal to the 7/2. The endpoint. This is where the ratio test would be equal to, you know, that quantity. The limit of an plus 1 over an would be equal to. So we have to go to the series and substitute to see what's going to be, what's going to be the result. So let's substitute. This is the most general case that we have. X equal to the 5/2. Go to the series, substitute. It's going to be sigma half. What was the series? Was 2 to the n, 2 to the n. Replace the x by 5/2. It's going to be 5/2 minus 3 to the n divided by the square root of n plus 3. 5/2 is 2.5 minus 3, so that gives -1/2. So it's going to be limit of 2 to the n. And that gives you -1/2 to the n. A square root of n plus 1, n plus 3. Carefully simplify this one. See what is this? This would be negative to the n, 2 to the n. I write it down in detail for you. Got to be careful for these simplifications. This is 2 to the n. A fraction raised to something, you raise the top, -1 to the n, and you raise the bottom. Okay, and this is going to be n plus 3. Now we get a chance to simplify 2 to the n and 2 to the n. So the leftover is sigma of -1 to the n, radical n plus 3. You know that this is a alternating series. You know that the Pn is 1 over radical n plus 3 and it is convergent. We accept it. It's a decreasing limit of the Pn is 0, so you claim that it is a convergent. It's a convergent alternating, but you have to tell us, you see, this is how you explain it. It's a convergent alternating series. So this means for x equal to the 5/2, your power series is convergent. We're not done. We have to check the other one. Okay, we check the x equal to the, so we check x equal to the 7/2. Go to the series again. So that gives a sigma of 2 to the n. Okay, 2 to the n. Replace the x by 7/2. 7/2 minus 3 to the n. Okay, over the square root of n plus 3. N plus 3, now 7/2 is 3.5. 3.5 minus 3 would be, again, 0.5, 1/2. So it's going to be sigma of 2 to the n, 2 to the n, and 1/2 again to the n. 1/2 to the n, and it's going to be radical n plus 3. Same thing, 1/2 to the n would be the top to the n and the bottom one to the n. So that gives you 2 to the n times it by, the top would be 1 to the n, the bottom one is going to be 2 to the n, and this is going to be the square root of n plus 3. Now 2 to the n and 2 to the n would be cancelled out, and negative 1 to the n would be 1. So that gives a sigma of 1 over radical n plus 3. You know that if you shrink it, it's like, you see, if you shrink it, it's like 1 over radical n, and this is what? This is 1 over n to the half. Is a divergent P series because P is 1/2. This is the way we do it, and we accept that. Is a divergent P series. So we didn't get it for, okay, so it's convergent, the power series is convergent for 5/2, that's divergent for the 7/2. So what's going to be the conclusion for this one? The conclusion is the radius of convergence, remember, was 1/2. Interval of convergence is a 5/2 and the 7/2, but at the 5/2 you close it because it's convergent. At the 7/2 you keep it open, which is going to be, so this is going to be the domain or the interval of convergence. So they are not difficult problems, but it takes time. So you've got to practice to know to make sure you're ready for it. Because whatever we want to do, we do it with these intervals. Okay, so I just stop here so that we can get the idea. Just do a couple of problems, examples, check your book. Then we come back and we continue. What we are going to do is we are going to look at as a function. You see, when you have this domain, means if you take any x inside, the limit of this series does exist. So we introduce a function. Then that function, we can work with it, we can differentiate it, we can integrate it. So we can differentiate the power series integrators with quite a nice one. So we have to, it's such a interesting tool. Okay, so go over this. Okay, I will give you a couple of more, I post a couple of more recording for you on this one. Okay, so we continue, let's say by tomorrow, Tuesday, and Wednesday. Wednesday again, I post another one for you. Okay, the plan is to finish this one before your next test, so that we can, if we can, so that we can check it, because the final exam would cover mostly the power series. Okay, that we can do. Okay, have a good one. I'll check your quiz to see what's going on with your quiz, and then we discuss there. Okay, have a good one. Take care. Bye-bye.